Good afternoon. Today I'm going to talk about robust design adjoint optimization of automotive components. I'm Paolo Geremia and I work with ENGYS. And this work was done in collaboration with my colleagues Yorgos Karpouzas, Eugene de Villiers, and Thomas Schumacher. Let's have a look at the agenda for today's presentation. So we'll start with an introduction to the adjoints methodology first, and then we'll guide you through an example case applied to topology optimization, then moving to robust design and multi-point definition and how it works in the context of topology optimization. And then I will talk about a real industrial case provided by VW. And finally, a few words as summary of the work done so far. A few words about the background behind the adjoint method. The project was originally commissioned by VW to ENGYS in 2009 with aim to develop a practical adjoint optimization tool that anyone can use. The work was done by Dr. Caster Optner by VW Research, and ENGYS performed the numerical implementation, testing, and validation in our software. The formulation is the continuous adjoint one, as opposite to the discrete adjoint formulation, which is available in other CFD codes. And the main focus was the real engineering application work. So this means supporting large-scale industrial problems, very often larger than 200 million cells for external aerodynamics problems. So accuracy is important on one hand, but on the other hand is not the only concern. We also need to make sure that performance, ease of use, and robustness are also important. So they are all equally significant to the end user. So this is why we built this package inside our HELYX software, and we call it HELYX-Adjoint add-on module. A few words about the continuous adjoint formulation, and this again comes from the theoretical work done by Dr. Caster Optner, and it starts from the Navier-Stokes equation, for which we have the momentum equation and the continuity equation, which are shown here. You can see that this is a standard CFD process that you solve using the finite volume method, and what you end up with is the V and P primal fields, what we call it primal fields. So it's basically the velocity and the pressure. So you can see the velocity contour on a cross section here of an external aerodynamics case. Then, by the same token, after some mathematical derivation, you get the adjoint CFD equations, which are solved at the same way you do with the same machinery components you use for the primal solution. And this is called adjoint solution. So we have a momentum and continuity equation, and we calculate U and Q, so which are the velocity and pressure dual fields. And this is how the velocity looks like in the dual adjoint solution state. It's opposite as the primal one, as you can see here. The final step is the computation of the sensitivities for both surface and volume sensitivities. So you can see here that after some quite some work in terms of derivation, you can express the sensitivities, which are actually the gradients of your design objective, which can be, for example, minimization of drag, increase of the mass flow rate, reduction of the maximum temperature, and so on, can be expressed as a function of V and U for both volume and surface sensitivities. So as such, the gradient computation is tremendously simplified. So you don't need to do finite difference or other differentiation methods to calculate the surface sensitivity. You just need to calculate two different finite volume solutions using the standard methods available. So in terms of surface sensitivities, what you get once you get the u and v velocities is what we call sensitivity map on the surface. So if you have, for example, a manifold case, and if you want to maximize the flow rate, you end up with a map of like it's shown here, where red means push the surface in to increase the mass flow rate, blue means pull the surface out to increase the mass flow rate. If you look at problems of external aerodynamics like the one shown down here, you have minimization of drag, you have red to pull in, to push in, sorry, and blue to pull out in order to minimize the drag. And by the same token, when you account for volume sensitivities and you want to solve for a topology optimization problem, then you have, for example, a duct and you want to minimize the pressure loss. This is what you do. So red means you have your cells which are free and they will remain fluid, whereas blue means you need to penalize the volume cells, and as such you can do, for example, you can add porosity to block the cells and to make it solid. And this is the sensitivity map for the volume cells, for the pressure drop objectives, and the maximization flow uniformity objective is shown down here. When it comes to set up a topology optimization problem, this is what you have to do. So you start from a specific design space and inlet-outlet assignment. Then you define the optimization objectives, and once you set up this in the CFD model, the CFD model algorithm will calculate the volume sensitivity. So it will penalize the volume cells according to the objective function, and will track the optimal interface using a level set immerse boundary method. So for example, here you can see you start from a specific packaging space, which is shown here, and then you have an inlet and an outlet, and you want to optimize the duct for pressure losses. And this is the optimal surface, which is changing during the simulation. You can see how the surface tracking is progressing. As a final result, you get a very smooth surface thanks to the level set, which can be exported to CAD format, and then you can view in the CAD, for example. This is only a single flow simulation. This is very important to keep in mind. Let's have a look at a real life example done from RevDop in Germany. So they took basically an airbox from VW 1.8 2.8 liters TDI TSI engine, and they took the real airbox and they scanned it, and then we did the optimization. This engine is in production since 2002 on different models like Audi, Seat, Skoda, and VW. The objective was to minimize the pressure losses. So we started from the available design space, from the original design, and we got the optimal surface, which we moved back to the CAD in order to make some minor modification for structural integrity and manufacturing. At the end of the process, we tested and compared the results compared to the OEM parts which was provided as a baseline design. So this is how the original design looks like. This is the CAD, and say in terms of pressure drop, we normalize to 100%. This is how much we get in terms of pressure losses as a reference. Then, using the adjoint, this is how we modify the design space, and this is what the tool predicted in terms of optimal surface. This is how this surface looks like. You can see all the material removed here. Okay. And the final shape that is, you can see here, material removed in the middle between these hills, you can see. And in terms of pressure losses, we gain a 33% compared to the original design. But then we went back to the CAD, and we have to do some minor modification in order to meet some manufacturing and structural integrity constraints. So we ran with the CFD, and we got a 26% improvement compared to the original baseline, which is still a good result compared to the baseline. Finally, they produced it, and they created this prototype, and we tested on the real car, and so we got the torque and the power of the engine for the modified versus the baseline. The baseline is the dashed curve, and the modified is the continuous curve. So you can see that for both torque and power, there's been an improvement in terms of results, which can be clearly shown also for the other engines. The first one was the TDI, this is the TSI, and you can see here with low RPMs the gain is more pronounced basically. Let's talk now about robust design. When we have a highly specialized design, so a design which performs very well for a specific operating point, this is what we have. We have a curve like of an input, and this is the response, and this is the peak. Okay, you can see in the curve. So a design which works really well on a specific point, but performance falls off quickly for off-design operations. So for example, here and here, it drops significantly. An example could be a track bike. So this one shown in the picture has no brakes, fixed gear, narrow and covered wheels, and the result it only was at 55 kilometers per hour indoors. And then, if we consider robust design, so we have an input which changes here, and the system response on the left here, and you can see this green curve. Okay, how we compare to the red one. So you can see that this green curve is optimized for several points of operation, not only one point, but for a series of points. So it loses peak performance, this one here, but performs good over a wider range of conditions. And an example could be a road racing bike, which has brakes, gears, and spoked wheels, as opposite to the previous one. When it comes to apply robust design to topology optimization, we talk about multi-point optimization. This works for multiple operating conditions. So, for example, you can have different flow rates at the inlet, or different combination of inlet and outlet. So you can have one inlet, multiple inlets, and multiple outlets, which are on and off in a selective way, and you can optimize everything in the same CFD model without the need of running different CFD models. And also, there is another example of multi-point optimization, which we will focus our talk today on, is about multiple ducts with prescribed inlet-outlet assignment. So, for example, here we have two ducts which we want to optimize. So we start from a spherical design space. We know the inlet and the outlet of each duct, and you can see here that we also want to have no overlap between the multiple ducts. So in terms of optimization problem, it's not trivial, because if you do one duct at a time, you will not end up with the optimal, real, ideal optimal shape. You need to optimize the two ducts simultaneously. And we can do this as part of the multi-point adjoint optimization in one go, and optimize both the ducts together. If we extend this, and if we look at a real industrial case, we have done a work in cooperation with VW Research for an HVAC system designed for a future car cockpit. So we have 6 different ducts, 3 operating points, structural constraints, and the idea was to optimize for pressure loss, minimum volume, and this also to account for make the manufacturing more easy, and also the assembly, of course. And finally, we had non-intersection constraints and uniformity objective for defrost. All the results are shown here, are shown with kind permission of VW. So this is the car dashboard and the domain extent as it looks like. This is the CAD. You can see here. Then moving at the optimization problem, we have 6 inlet-outlet pairs, which are color-coded. So blue goes to blue, red with red, and so on. And you can see here but we will only have inlet and the outlet. The duct does not exist yet, so we need to create it using this virtual HELYX-Adjoint Optimization tool. Then we also need to account for the obstacles which comes from a previous structural optimization done on the same computational methods. So in the area highlighted in gray color here, we cannot have intersection of a ducts created by the adjoint optimization tool. So this is a constraint. And this is how the topology optimization works for the 26 objectives. You can see here how it evolves. You can see the ducts taking shape from another perspective. And also you can see there is no overlap with the structural constraints. And one more time, here you can see how the solution progresses and how you end up with the optimal solution. So you can see how it's stabilized for the green duct as well. In summary, we have talked about a unique continuous adjoint formulation for topology optimization, which was developed by ENGYS, fully validated and deployed in industrial environment. And multi-point adjoint optimization is suitable for doing robust design and solving problems like efficient path finding, like we shown before. This is easy to set up using a single input deck file interface and is under constant development to improve efficiency. So thank you very much for your attention. If you have any questions, feel free to ask.